morning. I'm Paolo Marcatilli and this is a protein structure and computational biology course. Today's lecture will be about protein secondary structure. The learning objectives of today's lecture are to remember the definition of common secondary structures, to understand their properties, to understand the pattern of interactions that held secondary structures together, and to remember and understand the amino acid preference and local amino acid patterns that are associated with secondary structure. We have already discussed about the different levels of proteins, protein structure, starting from the primary structure to tertiary and quaternary structure. Today we will focus on the second level, secondary structure. We will discuss mainly about helices, different types of helices, then beta strands and beta sheets, and finally bands, loops, and turns. Let's start with helices. Now, the structure of a helix looks like this. It's, as the name suggests, an helical structure in which, as you can see here on the right side, that is held together by hydrogen bonds by oxygen and nitrogen of amino acids at a short distance in the sequence. The most common type of helix, that is the alpha helix, has an interaction pattern I plus 4, meaning that the oxygen of a residue has an H bond with the nitrogen of another residue. It's 4 residues after in the primary sequence. There are other types of helices, and most notably the 310 and the pi helix, that are defined by a different type of interaction patterns. We have to, as you can see, the alpha helix creates kind of an alignment of all the secondary structures, so of all the backbones, so that all the nitrogens are pointing in one direction, all the oxygen are pointing in the opposite direction. In this way, helices create a dipolar moment in the protein with a local partial charge along the helix. We will see that there is an amino acid preference and that we have specific amino acids in the helix at the end of the helix. Here we have the depiction of the most common helix types, the pi, alpha, and 310. The interaction pattern is for alpha, the most common I to I plus 4. For pi, I plus 5, so it's a bit more loose, it's a bit wider. Where the 310 helix is a bit more tight, I plus 3. Here we have the typical backbone angles that we find. For alpha helix we have a phi angle of approximately minus 65 degrees and a psi angle of approximately minus 40 degrees. Approximately the same angles are observed for pi and 310 helix. We have minus 30, minus 90 for pi, and minus 60, minus 30 for 310. If we display these in the Ramachandran plot, we will see that the alpha helix lives more or less in the middle of these right and the alpha helix region, where the 310 and the pi helix live more on the border. But this is not precise, so you will also find alpha residues that are in our alpha helical region, not exactly in this point, but around this region. Also remember that there is one Ramachandran plot region that is called the left-handed alpha helix. Now this name is a bit misleading because actually you will never find extended left-handed helices in any protein. So this region is actually mostly populated by residues that are either in loops or turns, we will see later, very few are actually in a left-handed alpha helix. Left-handed alpha helices are actually not stable or not favorable in proteins, since because of the fact that naturally occurring amino acids are L-amino acids, the side chain of the amino acid in a left-handed alpha helix would point towards the inner part of the helix, therefore making it impossible from a sterical, that means volumetric point of view, for extended left-handed alpha helices to exist. Also here we have to underline one final property of alpha helices. That is, there is actually an amino acid preference for the alpha helix. You can remember these as with the acronym MALEK, M-A-L-E-K. This is the most common residues that are found in alpha helices. Also, there are residues that are usually never found in alpha helices, such as proline and glycine. As an exercise, try to understand why we don't expect to have prolines and glycines in alpha helices. Finally, a large number of alpha helices are located on the surface or partially on the surface of a protein. Therefore, we can observe the so-called amphipathic pattern. So, amphipathic means there is one side or one part of the helix that is hydrophobic and one part that is hydrophilic. If we do this kind of plot in which, starting from residue 1, we kind of follow the helix by looking at it from above, and we see 1, 2, 3, 4, 5, you will see that the first residue is, in this case, it's hydrophilic, second is hydrophobic, third is hydrophobic, hydrophilic, hydrophilic, hydrophobic, hydrophobic, and so on and so forth. So you see that it emerges a pattern in which you have that 2 residues are hydrophobic and 2 residues are hydrophilic. Therefore, you can actually identify helices, or especially amphipathic helices, just by visual inspection. In general, however, these kind of patterns that are based on a size of 4 residues can help to identify helices from a protein sequence. Let's now go to the next element, that is beta sheets. Beta sheets are formed by beta strands. They are the main elements in this case. We have an example here, a thioredoxin, in which we have several elements that are not strands in green. If we remove those, we actually have a core that is formed by a beta sheet. A beta sheet is a kind of a flat element that is generated by 2 or more beta strands. So remember that in order to have actually beta elements like beta sheets, you need more than 1 beta strands. Individual beta strands are more rare in a protein. You see it's more or less flat, but actually each element can have a little bit of twist. So it is actually a bit more flexible than an alpha helix in that manner. Let's have a look at side chains. The strands, or these kind of arrows, are identifying the main chain. Side chains are pointing on either each direction, so up or down, one after the other. So you see that here in this case you have a pattern that it's more like based on a motif of 2 amino acids, up, down, up, down. And when, let's look for example at this region, residues that are close in the different strands are pointing in the same direction, and therefore they are also interacting. One important definition or characteristic of beta strands, or interaction of beta strands, is that they can interact either in a parallel fashion or in an antiparallel fashion. What is that is defining the this interaction, let's have a look here. This is the same representation in which we have the two parallel strands here and the two antiparallel strands here. As you can see, the hydrogen bond patterns is between, again, nitrogen and oxygen of residues that are far away in the sequence, and the hydrogen bond pattern of the antiparallel here, it's kind of more tight and more parallel, where the hydrogen bond pattern of the parallel strands, it's not so symmetric. So the hydrogen bonds are not so straight. What this means in terms of stability is that the antiparallel beta strands are generally a bit more stable than parallel interaction. We have another representation here in which you can see that the parallel H bonds are actually more ordered. The antiparallel H bonds are more ordered than the parallel ones. Also, we can clearly see here that strand interactions are non-local. So even though locally these oxygen and this nitrogen are nearby in the structure, they can be as far away in the sequence as possible. So they can have any number of amino acids between them. This means that in order to form beta sheets, distant parts of the protein in terms of the primary sequence have to come together. We have finally the last element. There are turns, loops, and bends. Practically, whatever is not an helix or not a sheet is defined as a loop or turn or bend. The general definition is here, loop. They are usually on protein surface, or most frequently on the protein surface. We see them here. And they are usually more unstructured because they have a less regular H bond structure than the other types of secondary structure. So to sum it up, we have to, today's lecture was about the protein secondary structure, their features, how they are defined in terms of hydrogen bond patterns, their characteristics, and the amino acids that we expect to find in secondary structure. Thank you.